Welcome everyone. I am Debashis Pachhar. Today I will be discussing about scalar leptoquark and flavor observables. This work is based on this paper and this work has been done with the in collaboration with Professor Bhupal Deb, Professor Suravati Goswami and Dr. Chan Mazumdar. First of all, I want to thank the organizers for giving me the opportunity to discuss about our work in front of the audience. So this will be this will be the brief outline of my talk. So first, I will give a motivation that why we are considering the scalar leptoquarks. Then I will discuss the scalar leptoquark model and its scalar sector. Then I'll talk about how this leptoquarks can generate neutrino masses and its effect on flavor anomalies. And then I will discuss the leptoquark contribution of neutrinoless double beta decay. Then I will show our results and then we'll summarize the talk. The standard model is a Gates theory, which is invariant under SU3 cross SU2 cross U1 Y gauge group, and it describes the three fundamental forces in nature. The prediction of the standard model has been verified by a numerous number of experiments. However, there are some observational shortcomings of the standard models, which includes neutrino oscillation. Neutrino oscillation is a phenomena which describes that neutrino flavors can oscillate into one another as they propagate. That means neutrinos can change its flavor between their creation and the detection uh, time. In the standard model, we have three flavor neutrinos. But here I have given the oscillation probability assuming a simple scenario of two flavor, and it can be generalized to three flavor very easily. And we see that the oscillation probability P alpha beta depended on the delta m square, which is the mass square differences of the neutrino. So neutrino oscillation does not provide any information about the absolute masses, but it gives the mass by differences of neutrinos, and also it depends on the mixing angle between the flavor states. So the three flavor oscillation scenario is characterized by two mass square differences and three mixing angles. And there is also a Dirac-CP phase, but the current oscillation experiment does not provide any conclusive indication that what is its exact value. Uh, okay. Uh, Also, precision experiment. There are some precision experiment whose result are not coincide with the standard model predictions. Out of them, the one is related to this semi-leptonic B decay to D and a lepton and a neutrino, antineutrino. So the RD and RD star is defined as the branching fraction of B to D tau nu uh, um, by B to D L nu, where L can be the first and the second generation lepton. This is the standard model diagram by which this process can occur in the standard model. This is the prediction of the standard model, and it found that the experimental value is 3.3 sigma away from the standard model value. Another is the B plus to K plus nu bar. So these are the diagrams which contribute to the standard model in this process. This can happen in the standard model through this penguin box and the tree level diagram. And this is the uh, standard model prediction of this branching fraction of this decay rate. But Bell 2 has recently measured this experiment has and found that the experimentally observed value is three times higher than the standard model predictions. The good news is that the leptoquarks, which are a hypothetical particle that can couple to both lepton and the quarks, they can address all these anomalous results that the standard model cannot explain. So we have So in this model, we have extended the standard model through two scalar leptoquarks, which is S1 and R2 tilde, and their standard model charges are given in the brackets. So this is the most general Yukawa Lagrangian in this model. And this is a term which is a part of scalar potential, which says that R2 tilde and S1, they can mix with each other with the standard model Higgs. So in this model, we have considered the baryon number and the lepton number of these new fields in such a way that the baryon number is conserved in the theory so that the proton decay cannot occur. And the lepton and this term, the mixing term of this R2 tilde and S1, it generates a lepton number violation in the theory. In the scalar sector, we have two leptoquarks like S1 and R2 tilde, so and they can mix. So this mass, the mass m square, that is the so this is not diagonal. It means that we need to diagonalize it through unitary rotation. And this x1 and x2 are the mass eigenstate of this S1 and R2 tilde, and this is the mass eigenvalue. The R2 tilde and S1 they can mix and generate the lepton number violation, which can generate the Majorana neutrino mass in this one loop through this one loop diagram. And we found that for the TeV scale leptoquark with the Yukawa coupling around 10 to the power minus 6, we can generate the observed neutrino masses in the neutron oscillation experiment. Uh, so these leptoquarks can also contribute to the flavor anomalies like RD, RD star. So this is the diagram by which the one-third components of the leptoquark can contribute to this B2D tau nu. So these are the operators which can be generated through these diagrams. And if we identify the Wilson coefficient, then we can calculate this RD and RD star, the theoretical observable, which is defined as RD by RDSM. And its deviation, the RD star, the deviation from one is dependent on this new physics contributions. This can all the leptoquark can also contribute to B plus 2 K plus nu bar, and these are the operators which contribute to this process. And then we can compute this theoretical observable RK nu, which is actually the ratio of the branching fraction of B plus 2 K plus nu by the standard model contribution of B plus 2K plus nu. As we have lepton number violation in this theory, this provides a nice framework to study the neutrinoless double beta decay, which requires the lepton number to be violated by 2 units. So as in this case, the neutrinos are Majorana. So this is the first contribution. This is the first contribution which contribute to neutrinoless double beta decay, and we call it the standard contribution. And apart from these, there are two contributions which depended on this neutrino mass insertion, or these three diagrams are dependent on neutrino masses, but these two diagrams where this leptoquark are involved are suppressed by the heavy leptoquark masses here. So among these three contributions, only this is the dominating, and the T half or the half-life of this neutronless double beta decay is dependent on this MEE standard, which is called the effective Majorana mass. Apart from these, we have other two contributions that depend on this leptoquark mixing. And in this case, the diagrams do not depend on the neutrino masses, rather they depend on the neutrino momentum. And these contributions are enhanced by PF, that is the neutrino momentum, typical magnitude of neutrino momentum by the typical magnitude of neutrino mass, which is 10 to the power 8. Now we want to compute these contributions through the effective field theory. So as the neutronless double beta decay is a low energy process, so it can be described by the low energy effective field theory Lagrangian. So this is the most general Lagrangian that we can write, where this current is originated from the standard model interactions, and all the other uh, beyond standard model interactions are encoded in this non-standard currents. So these two diagrams contribute to these two Lagrangians or these two currents. One is dependent on the scalar plus pseudoscalar, and the other is the vector and the axial vector. So with this, all the contributions we have computed this half-life of the neutronless double beta decay, and we have used, sorry, we have used the state-of-the-art tool NuDobe to compute the half-life of the neutronless double beta decay, and we have extracted the effective Majorana mass from the half-life. Now, what is our strategy? Here we have considered the most general Yukawa structure for this scenario, and then we have extracted this Y2, the other Yukawa coupling, in terms of the YL, the UPMNS parameters, the neutrino masses, and this R matrix using the Kasashibara type parameterization. But this is not exactly the Kasashibara type parameterization, because this R matrix here is not orthogonal. Rather, it satisfies this R plus R transpose equal to I. And the most general structure of this R can be written in this way. Uh, and we have chosen the parameter such that this mass of the leptoquark we have fixed at 2 TeV to avoid the collider bound. Then we have fixed this kappa around 200 GeV, and to avoid the precision T parameter constraints. Then we have varied the Yukawa couplings in the minus root of 4 pi to 4 pi range. And we have, for simplicity, we have assumed this R1 equal to R2 equal to R3, which is equal to R, and we have varied this from 10 to the power minus 2 to 10 to the power 2. And all the mixing angles here used in the UPMNS parameters are varied over their 3 sigma ranges, and the Majorana phases are varied from 0 to pi. With this choice, we have satisfied neutrino masses and mixings, and B meson decays, K decays, KL to mu E, mu to E conversion, the neutrino magnetic moment, and also the radiative decays of the charged leptons. And here we have considered two scenarios. We have, in case one, we have considered when RD star is anomalous, that is the current situation with the current values, and we have considered in case two a hypothetical scenario such that in near future, what if this RD star is found to be consistent with the standard model? Then what happens to the leptoquark parameter spaces? Now, in both the cases, we found a parameter space which is consistent with all the favor observables we have mentioned above. And then we have plotted the uh, effective Majorana mass, effective, as a function of the M lightest for both the cases, case 1 and case 2, that is with RD star and without RD star, considering the neutrinos to be either normal ordered or inverted ordered. And we found that for a substantial parameter spaces, the contribution of the leptoquark contribution is very high than the standard contribution, and we can use this stringent limit given by this Kamla and Zen uh, to further constrain the parameter spaces, leptoquark parameter space. And we also found that there are also the leptoquark contribution can be higher than the standard normal and lower than the standard inverted. So they can contribute to in this deserted region, which can be probed in the next generation experiment like Legend 1000 or nEXO. In the for the IO inverted ordering, what we find is that the most of the parameter spaces is already excluded by the zero nu beta beta. Only a few points are left from the Kamlan which can be probed in the next generation experiment. And we also found for the normal ordering, the the cancellation region is absent in this case. Here, in this two leptoquark scenario, we found that the value of this delta mu, which denotes the muon G minus 2 result, and in the y-axis we have plotted delta A, which is the electron G minus 2, they cannot be simultaneously large. It means that if you have a large value of this delta mu, then delta A is zero or close to zero or very small. And if you have large value of delta A, then delta mu is close to zero. And this tension occurred due to the constraint from radiative charge lepton flavor violating decays like mu to E gamma, tau to mu gamma, tau to E gamma, and B plus to K plus nu bar constraint. We also found that in the first case, that is when RD star is anomalous, the prediction of delta mu, that is which is defined as mu minus mu standard model, is very close to zero. That means that when RD star is anomalous, then the mu, the value of mu cannot be very far from the standard model value, which is actually the current scenario after the BMW result. So leptoquark uh, uh, actually favoring the BMW result. Summary. So here we have performed a comprehensive study on neutrinoless double beta decay, which arises from the leptoquark mediated diagrams. And in this case, we have considered two scalar leptoquarks, which is R2 tilde and S1. And we have performed a global parameter scan on the parameter space, considering two cases. In the first case, we have considered when RD star is anomalous, that is the current scenario. And we have considered a hypothetical scenario when RD star is not is consistent with the standard model. And we found a parameter space consistent with neutrino masses and mixing and all the flavor observable for B and K meson decays, charged lepton flavor violating decays like mu to E gamma, mu to E conversion, tau to mu gamma, and also the neutrino magnetic moments. The contribute and we find that the contribution of the leptoquarks can be bigger than the standard contributions and for both the mass orderings, and the current neutronless double decay constraint can further give tight constraint on some UCO couplings. We also found that for the both cases, that case 1 and case 2, uh, both delta mu and delta A, that is a muon G minus 2 and electron G minus 2, cannot be simultaneously large due to the other constraint coming from the charge lepton flavor violating decays and B plus to K plus nu. Thank you. Okay, so if you have any questions, so you can ask in the question answer session in the parallel session that will going to happen during 2 to 5 December. Thank you. I'll be happy to discuss or I will be happy to address some of your questions. Thank you very much.